Following lecture will cover sections 2.1 to 2.3 in the text. Chapter 2 deals with representing molecular compounds and different ways that we can represent these organic molecules that we'll be working with. Section 2.1 is an introduction to different ways to represent organic molecules. So the first that you're already familiar with is a Lewis structure. It shows the connectivity of all the atoms. It shows the bonds to each atom. A partially condensed structure simplifies our Lewis structure. And you can see that groups such as the CH3 group are bunched together. CH3 group is clustered. A condensed structure shows us that the CH3 groups are both attached to this carbon here. And because there's two CH3 groups, two identical groups attached to the same carbon, we can put them in parentheses. That carbon is also attached to a hydrogen, which is shown, and we put it in order. And then that carbon is also attached to an OH. The simplest representation that gives us the least amount of information is a molecular formula. This doesn't show any of the connectivity. There could be multiple constitutional isomers representing this molecular formula. So Lewis structures, partially condensed structures, and condensed structures all show the reader connectivity of the atoms in addition to the atoms present in the molecule. The first skill is being able to convert between any of these representations for a given molecule. So let's take a look at an example where we convert a condensed structure to a Lewis structure. We want to draw each group separately. So let's start by looking at the CH3 groups. The fact that they're in parentheses and that there's two of them, all right, indicate that this particular carbon atom has two CH3 groups. So all we're going to do is take them out of the parentheses and attach the CH3s to the carbon. That carbon also has a hydrogen. Okay, and at this point, we've got a partially condensed structure which can now be easily converted into a Lewis structure. So do one group at a time. You can start with the carbon in the center and just pick any of the groups. We have the CH3 group that can be converted to the Lewis form. You can take the next CH3 group, convert it to the Lewis form. We know that we've got a hydrogen atom attached to the carbon, so we can add that hydrogen in. The carbon is attached to an oxygen, and then we have that CH2, CH3 group, which is drawn on the end. You should also be able to convert back from the Lewis structure all the way back to a condensed structure. So, pause the video and give some of these a try. You should be able to convert the condensed structures to a Lewis with the first two, and then take the Lewis structures and convert them back to a condensed. When you're done trying these, come back to the video and check out my answers. Now that you've tried these, let's see how we come up with a Lewis structure for the first two. We have this carbon group, this carbon atom on the end, and it's attached to two hydrogens. That carbon is double bonded to another carbon atom, That carbon has a hydrogen. Now it doesn't matter if you put the hydrogen on the top or on the bottom. That carbon is attached to an oxygen, which is attached to another carbon that has two hydrogens. Make sure that all of your carbons have 4 bonds. That carbon is attached to a carbon here that has a hydrogen. And then that carbon has 2 CH3 groups. So let's draw the first CH3. I can draw the next one. Put your lone pair in, and you're done. The next molecule has a different group in parentheses. This is what we call an ethyl group, which we'll learn about in chapter 4. But there are 2 of these 2 carbon chains attached to our carbon. So let's start with this carbon. I know that it has a hydrogen. That hydrogen is attached to the carbon. And now let's put our 2 CH3 groups on there. So we have 2 of the CH2, CH3 groups. Running out of room here, we'll just draw it down there. All right, so this carbon is finished. That carbon is this one right here. Let's move on to the next carbon. I have a CH2, CH2, and then an OH. You can draw your lone pairs in. Moving along to the next example, we want to convert a Lewis structure to a condensed. We notice that we have a carbon. Let's start here, and we have 2 CH3 groups and that hydrogen. Well, we've seen what to do with this before. Here's your carbon with the hydrogen, and we can put those 2 CH3 groups in parentheses. That carbon is attached to a C. Is attached to a CH2, and that is attached to an OH. In the next molecule, we have a CH3 attached to a carbon that has a hydrogen and an OH. Next in line is a CH2. We have another CH2. We have a CH with a Cl. And finally that CH3. The most common representation in organic chemistry is called a bond-line structure. We need bond-line structures for large complex molecules, where drawing Lewis structures would be impractical. Take the example below. Drawing this is tedious and time-consuming. Drawing a bond-line structure simplifies matters. So the bond line structure is the main representation that chemists use, and this is what we'll be using from here on out. So here's how to read a bond line structure. I have several examples up top, and let's read the characteristics of bond line structures and refer back to each of the examples. So each corner or endpoint represents a carbon. Let's look at our first example. The endpoint is a carbon. A corner is a carbon. Carbon, 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 and carbon. You can see we have 6 carbon atoms. The carbon-hydrogen bonds are omitted because it's assumed that carbon should have enough hydrogens to complete its octet, making 4 bonds for each carbon atom. In the second example, we have 1, 2, 3, 4 carbon atoms, and in this case we have a double bonded carbon. You can see that the end point has a CH3 group, 3 carbons. The second carbon has a hydrogen. Third carbon has 1 hydrogen. And the fourth carbon has 3 hydrogens. So if you've noticed, all of the endpoints have CH3 groups. If you have a corner without any double bonds, then it's a CH2. A corner that has a double bond is a CH. We have a special case when we have triple bonds. We have to make sure that triple bonds are drawn with a linear geometry. Why? Because triple bonds are sp3 or sp hybridized and they have 180-degree bond angles. We need to consider the geometry and represent our bond line structures as closely as possible to the true geometry. The first skill dealing with bond line structures is just being able to count the number of carbons and hydrogens. So given a bond line structure, you need to be able to count first the carbons, and then let's take a look at the hydrogens. So with the carbons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Remember, each corner or endpoint counts as a carbon. It might be helpful, in order to do the hydrogens, to convert your bond line structure to a Lewis structure. This will help you keep track of your hydrogens. So atoms that are non-carbon groups will always have the hydrogen shown, like this sulfur. So if you count your hydrogens then, or you can draw them in, we have hydrogen, hydrogen. Remember, carbon has 4 bonds, so there's no hydrogen there. There's 1 hydrogen here. We have no hydrogens on the next carbon. We have 3 here, 1, 2, 3. And then moving along, we have 1 hydrogen. No hydrogens on the next carbon. No hydrogens on the next one. We have 3, 1, 2, 3. 1, 2, 3. 1, 2. 1, 2, 3. So there's a couple different ways we can approach that. I'd like you to stop the video and give the next couple examples a try. When you come back, I'll give you the answers and show you the number of carbons and hydrogen atoms. All right, hopefully you've had a chance to give this a try. For our first problem, first molecule, there are 8 carbons, and there are 10 hydrogens. For carbons, we have 1, 2, 3, 4, 5, 6, 7, 8. And we can draw our hydrogens in. 1, 2, 3. 4, 5, 6, 7, 8, 9, and 10. For the next molecule, there are 6 carbons and 12 hydrogens. So for carbons, 1, 2, 3, 4, 5, 6. And if we draw all our hydrogens in, giving each carbon 4 bonds, we'll see that we get 12. For the next molecule, there are 7 carbons and 6 hydrogens. For carbons, we have 1, 2, 3, 4, 5, 6, 7. Then putting in our hydrogens, 1, 2, 3, 4, 5, and don't forget the one on the oxygen, 6. When we draw bond line structures, make sure that carbon atoms in a straight line are drawn in a zigzag. This is maintaining a more accurate bond angle. If you recall, the VSEPR theory tells us that bond angles for sp3 hybridized carbons are approximately 109.5. For sp2 hybridized carbons, the bond angles should be approximately 120 degrees. So this is an incorrect representation because that bond angle is nowhere near 120 degrees. And the direction of single bonds is irrelevant because single bonds can rotate. These two structures are the same. If I rotate that bond right there, if I rotate this bond, I get this same structure here. And we can rotate this bond back and rotate that bond and get back to our original structure. Any atoms other than carbon that contain a hydrogen should be labeled with all of the hydrogen atoms. Do not omit hydrogens on atoms other than carbon. And finally, never draw a carbon atom with more than 4 bonds. Do not exceed the octet rule. All right, in our next example, let's convert the Lewis structures and the condensed structure to a bond line structure. So pause the video, give it a shot, and when you come back, I'll give you the answer. All right, hopefully you've had a chance to give this a try. The answers for the following are ROH attached to a carbon, attached to a carbon, attached to an oxygen, we have our CH2, and we have our triple bond to another carbon. Now it doesn't matter which direction you draw this necessarily. I'll draw it down, and then you have your 2 CH3 groups. For the bottom structure, converting that to a bond line, we have our 2 CH3 groups, our double bond, another CH3 group, and finally CH2 and the CH3. Section 2.3 deals with the identification of functional groups. A functional group is simply a characteristic group of atoms or bonds that has predictable behavior. So organic compounds can be classified as functional groups or based on their functional groups. So there's a table at the end of the notes that has a list of the functional groups that you need to know. We're going to go through these. But before we get to the actual functional groups, let's talk about the simplest organic molecules. These are the alkanes. Alkanes are the simplest hydrocarbons. A hydrocarbon is just a molecule that contains carbon and hydrogen. So alk stands for hydrocarbon. Ane tells us that we're dealing with only single bonds, that there are no double or triple bonds. When you see an R group, that means it is an alkyl group or a generic bunch of carbons. Another way to think of R is just the rest of the molecule. For saturated hydrocarbons, we have a general formula that tells us that each carbon contains the maximum amount of hydrogen atoms without exceeding the octet rule. So C to the N, H to the 2N plus 2. For example, if you have a hydrocarbon with 3 carbons, then the number of hydrogens should be 2 times 3 plus 2, so you have C3H8. That would be propane. Make sure you're familiar with the saturated straight chain hydrocarbons for carbon chains of length 1 through 10. You want to know their names as well. 1 carbon is meth, 2 is eth, 3 is prop, 4 is bute, and 5 through 10 should all be prefixes that you're familiar with. Pent, hex, hept, oct, none, and decane. And notice how the number of carbons, right, that correlates. We can plug that in for our N value. And do you see the pattern for the number of hydrogens? How as we increase the number of carbons by 1, we increase the number of hydrogens by 2. It goes 4, 6, 8, 10, 12, and so on. Carbon atoms are also classified by the number of other carbon atoms bonded to it. So a primary carbon has 1 other carbon bonded to it. A secondary has 2. A tertiary carbon has 3 other carbons bonded to it. And a quaternary carbon has 4. So let's take a look at our primary carbon. You can see that this carbon is attached to 1 other carbon atom. For a secondary carbon, this carbon is attached to 2 other carbons, 1, 2. For a tertiary carbon, that carbon is attached to 3 other carbons. And for a quaternary carbon, this carbon atom is attached to 1, 2, 3, 4 other carbons. It's one way that we can classify carbon atoms. The first functional group, and yet another class of organic molecules, are the alkenes. Alkenes are simply hydrocarbons that have carbon-carbon double bonds somewhere. Their general formula is C to the N, H to the 2N, where N is the number of carbon atoms. Alkenes have a pi bond between 2 carbon atoms in the chain. There are 2 types of alkenes that we'll be discussing this semester, cis and trans alkenes. And if you recall when we talked about pi bonds do not rotate, right? They restrict the rotation. So alkenes have their groups locked into place. We have cis, where the non-hydrogen groups are on the same side, and trans, you can see our non-hydrogen groups are on opposite sides. Alkynes are hydrocarbons with a triple bond. Their general formula is C to the N, H to the 2N minus 2. And a few examples, you don't have to memorize the names, but a few examples of hydrocarbon alkynes are ethyne, pentyne, and 2-pentyne. An important functional group that you should be familiar with after today's lesson is an aromatic group. It's simply a hydrocarbon that has an alternating double and single bond. Now the aromatic groups, you're going to see these in our first experiment with melting point and TLC of the analgesics, is that all of your analgesics have these aromatic groups, a ring with alternating single and double bonds. And typically we're going to see a 6-membered ring for now. The aromatic functional groups to know is specifically the phenyl group or a benzyl group. But in identifying these in a molecule, you can simply call it an aromatic or an arene. The simplest example here is a benzene ring. These are flat, all of the carbons have pi bonds, they're sp2 hybridized, and here's our structure. The next functional group you should be familiar with after today's lesson is a haloalkane or an alkyl halide. It's just a halogen. Remember, halogens are group 7 on the periodic table. Fluorine, chlorine, bromine, and iodine. So just take any hydrocarbon, replace one of the hydrogens with a halogen atom. We have an alkyl halide. A few examples. We have methyl bromide, so we have that halogen attached to a carbon. We have ethyl chloride, we have a chloride attached to a carbon. Now this is called a primary alkyl halide or a primary chloride. We determine that it's primary because the carbon with the halogen attached to it has one carbon attached to it. Let's look at the next one with the iodine. It's secondary because the carbon with the halogen is attached to two carbons. It's secondary. So ask yourself, how many carbons are attached to it? Look for the carbon with the halogen and ask yourself how many carbons are attached to it. Let's look at tert-butyl bromide. Find the carbon with the halogen and ask yourself how many carbons are attached to it. 1, 2, 3. So it's a tertiary bromide. Alcohols simply have an OH group. Now we're going to see the OH group again with carboxylic acids, but an alcohol is simply an OH group on a carbon chain. The OH group is also called a hydroxyl group. A few examples would be ethanol. That's a primary alcohol because if we look at the OH group, find the carbon it's attached to, and ask yourself how many carbons are attached to it. Just one, so it's primary. Cyclohexanol is a secondary alcohol because we have our OH group attached to a carbon. Ask yourself how many carbons are attached to it. 1, 2. That makes it secondary. We can have tertiary alcohols, and we can even have aromatic alcohols in which the OH group is attached to an aromatic ring. The next functional group is an ether. It's basically an oxygen sandwiched in between two carbons. We have our two carbon atoms sandwiching an oxygen atom. It can take a variety of forms. We have an oxygen sandwiched in between two carbon atoms. Amines contain nitrogens. A nitrogen atom can be attached to 3 other groups in its neutral state. Now, 1, 2, 3, they can be alkyl, meaning carbon, or it can be hydrogen. And we can classify amines as primary, secondary, tertiary, or quaternary. The classification system is a little bit different than the one we discussed previously. For a primary amine now, this is different. Find the nitrogen and ask yourself how many carbons are attached to it. Just one. It's primary. For the secondary, let's take a look at the nitrogen. Ask yourself how many carbons are attached to it. 1, 2. And for a tertiary amine, if we look at our nitrogen, ask yourself how many carbons are attached to it. 1, 2, 3. This is a little different, so that's tertiary. And quaternary would be attached to 4 different carbon atoms. Quaternary amines are always positively charged. They have a positive formal charge. The next set of functional groups have something called a carbonyl group. Now this is where things often get confusing for students. There are many carbonyl groups, or there are many carbonyl containing functional groups, and initially they all kind of look the same. But what I want you to do is look for your carbonyl group and then look for whatever is attached to it. That's going to help you identify the specific functional group with that carbonyl group. So the first is an aldehyde. We can also represent it as CHO, not COH. An aldehyde has a carbonyl group directly connected to a hydrogen. An example is benzaldehyde. You have your carbonyl that's attached to a hydrogen. Everything over here, this is your R group. So we have R, the carbonyl, and then the carbon attached to the hydrogen. A ketone is simply a carbonyl in a carbon chain. So another carbonyl containing functional group, and R is carbon something, right? Do we see the carbon chain? And we have our carbonyl group sandwiched in there. The carboxylic acid is the next functional group that contains a carbonyl. Now, carboxylic acid can be identified. You look for your carbonyl. What's next to it? An OH. This is not an alcohol as well. It's special. So the characteristic of carboxylic acid is that we have that carbonyl connected to an OH. An example would be acetic acid. You see the carbonyl and the OH attached to the carbonyl carbon. Another way to represent a carboxylic acid is COOH or CO2H. The next functional group containing a carbonyl is an ester. So it's RCOR. It's always a carbon here. Carbon something. An example would be ethyl acetate. So we have our carbonyl attached to an OC something. We can represent it as COOR or CO2R. Remember, identifying these functional groups is all about looking what's next to the carbonyl. We have an OH or an OC something. An amide is yet another carbonyl containing functional groups. Remember, an amine was just a carbon attached to a nitrogen, and then, we could have hydrogens, and that would be a primary amine. We can also have amides in which the carbonyl is attached to a nitrogen. A primary amide is where the nitrogen is attached to only one carbon. A secondary amide is where the nitrogen is attached to 2 carbons. A tertiary amide has the nitrogen attached to 1, 2, 3 carbons. The next functional group is an acyl halide. We have a carbonyl, and it's attached to a halogen, an element from group 7. Next, we have thiols. Like an alcohol was an oxygen attached to a hydrogen, a thiol is simply a sulfur attached to a hydrogen. Sulfides are kind of like ethers, but we have a sulfur in the middle. Now, the first important skill is to be able to look at a Lewis structure and bond line structure and identify the functional groups present. So, what I would recommend doing is using the table at the end of the notes and look for the patterns. Eventually, I recommend making note cards and memorizing the patterns. There are several apps on the Apple Store and the Google Store that can help you to identify functional groups. There are a variety of different Quizlets out there that you could download that would quiz you on functional groups. So what I'd like you to do is pause the video and look at the table at the end of the notes and try to identify the functional groups. Each of these structures contains only one functional group. When you're done, come back and check your answers. All right, hopefully you've had a chance to identify the functional groups present in each molecule. So let's go through and see what we have. In our first molecule, we have a carbonyl next to a hydrogen. That's an aldehyde. In our next molecule, we have a carbon attached to a halogen atom. No carbonyl. This is an alkyl halide or a haloalkane. In the next functional group, we have a carbonyl attached to an OH. That's a carboxylic acid. Next, we have a carbonyl attached to a nitrogen. That's an amide. In our next molecule, we have just a carbon-carbon double bond. That's an alkene. Next, we have a nitrogen attached to a carbon with no carbonyl. So that is an amine. Make sure you differentiate amines from amides. Amides have carbonyls. Amines, no carbonyl. So you can think of the N in amine, that stands for no carbonyl. Not really, but you can think of it like that. Next, we have a carbon connected to an SH, that's a thiol. We have a carbon connected to an OH, that's an alcohol. In the next example, we have an anhydride. In the next one, we have an oxygen sandwiched in between two carbons. That's an ether. Now, esters have carbonyls. It looks similar, but an ether has no carbonyl. We have a carbon-carbon triple bond. That's an alkyne. And here we have a ring with alternating single and double bonds. That's an aromatic or an arene. Down at the bottom, we have a sulfur sandwiched in between two carbons. That's a sulfide. Carbonyl group next to a halogen. That's an acyl halide. Next, we have a carbonyl next to an OC. That's an ester. And finally, we have a carbonyl sandwiched in between two carbons, or it's in a carbon chain. That's a ketone. Next, we're going to step it up, and we're going to look at bond line structures and try to identify the functional groups in each of these bond line structures. So, pause the video, give it a shot. When you come back, you can check your answers. All right, hopefully you've had a chance to try this. Our first functional group, we have a COH, that's an alcohol. Next, we have a carbonyl next to a nitrogen, that's an amide. We have a nitrogen that's attached to two carbons, so that technically is a secondary amine, but you can just call it an amine. The SH group is a thiol. We have an alkene, carbon-carbon double bond. Next, we have a carbonyl next to an OC something. That's an ester. And finally, on this molecule, we have a carbonyl next to an OH. That's a carboxylic acid. In our next molecule, we have an oxygen atom sandwiched in between two carbons. That's an ether. We have a carbonyl that's in a carbon chain, so that's a ketone. There we have an alkene. We have a ring with alternating single and double bonds. That's an aromatic or an arene. We've got a carbon-carbon triple bond. That's an alkyne. And finally, we have a carbonyl next to a hydrogen. That's an aldehyde. So, it's going to take some time to get used to identifying these. You first need to learn the patterns and then practice finding them. I have additional practice problems and worksheets posted on Blackboard in the supplemental materials folder, so please check those out and give them a try.